Everybody, thanks for coming out tonight. This is the Ocean and Coastal Resource Management Speaker Series that is sponsored by the Center for the Blue Economy. My name is Jason Scourse and I am the director of the center. And again, great to have you all here. Tonight we are very happy to have one of our own, Dr. Brendan Kelly. Brendan is one of the country's, probably the world's premier Arctic scientists. And Brendan and I have been in some interesting conversations over the last couple of years about, the amount of natural science knowledge that people need to influence policy. And this is very germane to our program because we have a very social science heavy program here. And we're trying to train the next generation of leaders. And as you can imagine, there's a huge amount just in economics and politics and behavior design and policy process and data analysis and GIS. There's a million things, right? So it's impossible for everybody here to also be trained in all the details of natural science for climate change and biodiversity. So we have to be very strategic about what we teach them. And so Brendan and I have been in these conversations, and this talk will be some of his initial thoughts on kind of how that interface, that natural science policy interface works. He will not just be speaking to our students. He knows there's a lot of community members here, and he'll be using some of examples from his own work. Brendan is chair, he's the leader of the SEARCH program, which I'm not going to try to get the acronym right, but it's basically the key Arctic science research program for the United States. And Brendan was working out of the White House in the Obama administration when we had a president who seemed to care about science, but hopefully we will get one again. So with that, let's give a warm welcome to our very own Brendan Kelly.
Thanks, Jason. I appreciate it. Can everybody hear me okay? So SEARCH stands for the Study of Environmental Arctic Change. And this is a collaborative study by the University of Alaska and Rutgers and Woods Hole and Northern Arizona University and University of Colorado and others. And it's a collection of social and natural scientists who are trying to bring together what they individually know about Arctic change to understand its fullest extent. So what you're looking at here is a briefing we did in the Senate a couple of years ago before the Arctic and Ocean caucuses. Here's a staffer. He's reading briefs that SEARCH has written about specific issues in environmental change in the Arctic. And we've intentionally had the content area experts write those briefs, and we've had people who aren't content experts but understand what clear writing is like, edit them so that they were accessible and usable. So as one of the responses we've had from the Hill to having shared these briefs with them is they've asked us on a number of occasions to come and do briefings. This was one of those briefings. So sitting at the table there, you see scientific experts in permafrost science, in anthropology, in atmospheric science, in sea ice modeling, and in land ice processes, glaciers and ice sheets. Any one of those people could have easily filled, an hour-long lecture, and fortunately they didn't. Instead, what we did was we produced one short, single, consolidated briefing of about 12 to 15 minutes, and then we opened up the rest of the time for questions. That's a much more useful and effective way we find in many policy settings, certainly on the Hill. But before kind of going into more detail about what we're doing with SEARCH now, I thought it would be helpful to get to know something about my audience. I know some of the people here. Thanks for coming. But particularly interested in knowing who here either works in environmental policy or thinks that they might someday want to work in environmental policy. Could I just have a simple show of hands? All right, good. How many people here have a degree in science? And how many don't have a degree in science but feel like they know a fair amount about science? You can raise your hand. Great, excellent. So this is a good group because, as Jason alluded to, what I'm particularly interested in learning from you is sort of your perspective on this question of what kind of science literacy do we think we need for people working in an environmental field? What else do I want to say about that? A couple other things. Well, that's I guess essentially it. I really want to provoke that discussion by sharing 3 examples of, from my experience of bringing science to policy. And in each of those examples, I'm going to try to do 2 things. I'm going to try to tell you something about the Arctic environment and how it's changing. And the second is to reflect on the kind of knowledge that was needed to inform policy of those individual experiences. So my first case study, if you will, involved seal conservation. And I sometimes refer to the many years, decades actually, that I spent studying Arctic seals as the head down period of my career. So there you see me, head down, looking into a snow cave in which ring seals give birth. The caves are typically snow-covered and not visible. Here the cave is collapsed prematurely, but normally you wouldn't be able to see that cave under the snow. It would just look like all the surrounding snow. Fortunately, my Labrador retrievers know how to find those locations by smell. Ring seals are small cousins to harbor seals like we have around here, but ring seals feed under the ice and then surface to breathe in holes that they've kept excavated in the ice by scratching at the ice. The holes become snow covered early in the year and remain that way through much of the fall, winter, and spring. And where the snow has drifted to sufficient depths, they'll reach up above that breathing hole and carve out a cave in the snow. And then they come out of the ice and rest on the top of the ice, encapsulated in this snow cave. The pups are born in there and spend the first couple of months of their lives in those snow caves. Well, I didn't invent this method of finding seal holes. The Inuit did, and I learned from Inuit in Canada how to find these seal holes using dogs. I learned a lot more from them as well. Let's see if I can get this to. The Sikumi were the people of the sea ice, and they lived on the ice for much of the winter every year. And they depended on ring seals for food, for fuel, and for skins that they used for many purposes, including clothing, ropes, and other items. And their dogs showed them where to find the seal holes. Maybe I can stop it there. No, I can't. Sorry about that. Stop that entirely. Let's see if we can get it going again. Here we go. The dog is smelling the seal's hole underneath that snow. And what Monarch's doing here is he's using this probe, sort of like an avalanche probe, to find where there's water instead of ice under there. And now what he's done is he's taken a little piece of hair that he's frozen onto this little piece of bone, and he's planted it in that probe hole, and now he's going to watch that for as many hours as it takes for that little hair to start moving up and down to indicate that the seal is breathing beneath him. Well, now this is what's going on in between seals breathing in the hole as they're underneath that ice, foraging for plankton and fish. So it's the ability to maintain those breathing holes into a couple meters of ice that allow these seals to spend all winter in the high Arctic. the seals surfaced in its breathing hole under the snow. And then we climb out to the surface of the ice, but inside of that, okay? Well, it's not just people, but other predators, including polar bears, also seek out ring seals. And in fact, about 90% of what polar bears eat are ring seals. So this species, ring seals, is culturally and ecologically central to this ecosystem. Neither polar bears nor the Sikuyu could have colonized the Arctic without the presence of this seal. Well, my initial ring seal research focused on disturbance by seismic testing associated with offshore oil development, but also branched off into studies of under ice navigation, predator avoidance, methods of counting the seals, and ultimately climate change. So when NOAA was petitioned to list ring seals under the Endangered Species Act, they asked me to lead a team that had to review everything we knew about the species and their vulnerability to climate change, to industrial development, to shipping, and other threats. Well, research that I'd already done with scientific and Inuit collaborators had demonstrated that ring seals need snow cover of at least 25 centimeters to successfully rear their young in those snow caves. So everything inside of the box, everything in the greens on up to the reds, is sufficient snow cover on the ice, but everything on the left-hand side or in the blues is insufficient snow cover. The consequence of having insufficient snow cover is those pups are exposed prematurely to both predators, that's not a good thing, or to extreme temperature events. So increasingly now we get these abrupt warming events before the pups are fully cooked, if you will, ready to go. The snow collapses, the pups get wet, and it gets cold again and they freeze. So in order to forecast what was going to happen in the future, we had to do further collaborations with modelers, with climate modelers. And eventually we were able to show using 10 climate models that those models consistently forecast that by the end of the century, there will be 70% less suitable habitat for rearing pups than there is now. So this period is showing the period 1981 to 2000. Here's the projections for 2081 to 2100. And you can see from the color bars there's very, very little suitable habitat. And this turned out to be key in the listing of the species under the ESA. But I want to make the point that it wasn't sufficient to have the data. It was also necessary for us to be able to make it clear to Jane Lubchenko, who's then the administrator, and judges who heard subsequent court challenges, they had to fully appreciate the connection between the seal's dependence on snow and the forecast for its future. So the point I just want to emphasize is the data were very important, but writing and briefing very clearly was equally important. And I would say that's, I have lots of science colleagues who do wonders with data, but maybe not so much with clear communication. So now my head started coming up, and I began spending less time on the ice and more time bringing science to policymakers. I advised indigenous communities in Alaska, the state and federal government, international bodies, and NGOs on environmental changes in the Arctic. And while it's certainly the case that lots of people are interested in polar bears and seals, decision makers need to know not just how the Arctic is changing, but why. And we've come to understand that the environmental change in the Arctic is primarily being driven by, guess what, greenhouse gases in the atmosphere. Moreover, the warming signal that we're seeing around the globe from greenhouse gas concentrations is amplified in the Arctic due to a number of peculiarities of snow, sea ice loss, permafrost thaw, such that the Arctic is warming 2 to 3 times as fast as the planet as a whole. So what you're seeing there is this, I don't know if you're familiar with reading these, but this is what's called the surface air temperature anomaly. So what's the dotted line here, if you imagine, that's the average temperature during the period of 1981 to 2010. And then these other squiggly lines are, in the case of the black line, the actual observed temperatures in this period from the 1950s on up to recent dates. And the blue line is the changes seen in the Arctic. And so what you see is, while there's been a warming trend relative to the long-term average in the mid-latitudes, there's a very, very steep, much steeper warming in the Arctic region. So before turning to my second case study, though, I want to venture down a small rabbit hole, or maybe I'll say a seal hole, and just make sure that we can all sort of explain the essence of why greenhouse gases warm the planet, unless we're interested in bringing science to policy. Well, if you ask that question of a scientist, their impulses often would be to answer in terms of chemistry and physics, and that's fair enough, unless your audience really needs is the essence of the problem, not the details, which is, of course, often the case when you're talking with policymakers. This is a challenge because these are sophisticated people. They have, it's not a lack of intellectual sophistication, it's a lack of time and bandwidth, that they just don't have time to hear all the cool things I've found in all those years studying seals, right down to the chemical level. So the challenges for you and me when informing environmental policy is to convey succinctly and clearly the relevant take-homes without a lot of extraneous information. So I would argue that whether you studied chemistry or not, to work in environmental policy, it would be useful to understand and be able to explain the role of a few particular elements on this periodic table. And specifically, these elements are important to know something about from an environmental perspective because they are essential to every living thing on the planet. Okay? So carbon, hydrogen, oxygen, and nitrogen are the stuff with which most biological tissue is made from. And carbon, hydrogen, oxygen, nitrogen with phosphorus is the stuff that makes up DNA, right? The informational molecules of all of life. It's also important to recognize that many of those elements are vital in driving climate. Another reason why it might be good to understand something about that basic chemistry. So this kind of crazy looking table is really taking some of these elements, some in the form of molecules, and it's looking at their percentage of the atmosphere that's made up of those gases. And then over here we're looking at the concentration, these are in parts per million by volume, in the year 1748 and in the year 2018, okay? And what you can see is that 99% of the atmosphere is made up of oxygen and nitrogen. And oh, by the way, they're really not changing. That's a very stable percentage. It's also the case that they don't have any particular impact on the temperature or the ability of the Earth to hold in heat. And this has to do with, not very complicated, most of the molecules that are made up of two atoms, and that's the case of nitrogen and oxygen as the gases, and two atoms of nitrogen or two atoms. Well, these molecules that are made up of two atoms bonded together are not much impacted by being interacting with solar radiation. But many molecules, I should say, that are of 3 or more elements are. And so things like water, H2O, CO2, methane, CH4, nitrous oxide, those have 3 different atoms making up those molecules. And when solar energy hits those in the atmosphere, those bonds between those 3 elements begin to vibrate. And that vibrational energy then gives off energy in the form of infrared. And that infrared energy is, much of it goes back to the Earth. Okay? So that's energy that was on its way back at us to space and reflected from the planet. And instead, it's now, some of it's returned to the planet. And that is the essence of why we are now accumulating more energy as a planet than we're letting go of. Hence, we're warming overall. And I guess what I neglected to point out is that the concentrations of carbon dioxide and methane are increasing. That's also seen on this table, unlike nitrogen and oxygen. But we all know why that's happening, right? Because that's coming from emissions, primarily from fossil fuel burning. Okay, so much for my trip down the seal hole. You take all of that, the net effect of taking in more heat than we're sending back to space is that we are warming the planet. We're taking in an extra 0.58 watts per square meter over the surface of the entire Earth. Tiny little amount until you add it up over the entire size of the Earth. So it's ironic that these trace gases in the atmosphere are increasing enough. They're still trace gases, but they're having a huge effect on the energy balance of the whole planet. Well, increasingly now, we're in a world where we have the computational ability and the scientific prowess to be able to take all of the exchanges of heat between the atmosphere and the ocean and the land and all the feedbacks, and there are many, and actually write them out in equations straight from the physics textbook, put them into giant computers, and make really good forecasts of where this is going. And we know these are really good forecasts for a number of reasons, including we can go back in time. We can hindcast by looking at concentrations of these gases trapped in ice, in giant ice cores, go down back hundreds of thousands of years, both in Antarctica and Greenland. And we can date those gas bubbles, and we can break down the composition by those gases I showed you. And what the models are able to do is very, very accurately reconstruct, based on first principles, what those ice cores show. That gives us some good confidence that when we look forward and we say where the climate's headed in the rest of the century and beyond, we're probably right. It's not perfect, but it's a whole lot better than just guessing. We're just assuming that, well, things will follow some kind of pattern like they have historically. That's not a good assumption anymore. That's quite clear. So this finally leads to case number 2. One of those feedbacks I mentioned has to do with carbon coming out of permafrost. And if you've never seen permafrost, here it is. And this is just outside of Fairbanks, not far from our university. This bluff is sloughing and giving us a nice cutaway view of permafrost. So the first thing to know is that this upper layer, just this layer here, is what we call the active layer. This is soil that freezes in the winter, thaws again in the summer, freezes in the winter, but it's active in that sense, it's changing. Everything below that has been frozen since at least the Pleistocene. And so what you're seeing in this particular cutaway is soil, permafrost soil, which is loaded with carbon and ice wedges. And so when the active layer gets deeper, we start thawing further and further down. We're thawing two things. We're thawing ice and we're thawing soil. Well, if you thaw ice, it turns to water, it's going to run away. And so you're going to have this big void here and the ground's going to collapse where that ice was. But when you thaw the soil itself, it's like taking a hamburger out of the freezer and thawing it. It doesn't melt and run away. You take an ice cube out, it melts and runs away. So think of the soil as thawing, not melted. So I think there are two things to consider when conveying to policymakers the role of permafrost in affecting ecology. The first is, why is it that permafrost is emitting carbon? And the second is, how much is likely to come out of it? And the reason it's letting go of carbon is because this soil has a lot of dead plant matter in it. And just like your meat in the freezer, your vegetables in the freezer, they're protected from degradation by bacteria while frozen. But when you thaw this and it gets warm enough, then the bacteria get terrific. And they just like, if you leave it on your counter, it'll start going bad. That's because of bacterial degradation. So the bacterial degradation that happens on the organic canopy in permafrost, once it thaws, one of the byproducts of that decomposition, well, two of them were CO2 and methane, and that was released into the atmosphere. So that's how it happens, that's why it's happening. But how much is there? That's the harder question. We have a good idea how much is there. There's twice as much carbon locked up in northern permafrost as exists in the atmosphere today. So pretty clear, we wouldn't want all of that to escape. We know some of it's escaping, we just don't know how much. Our best estimate right now is that something in the order of an additional 150 million metric tons by the end of the century. That's something like close to 30 years of US emissions at our current rate. So that'll give you some idea of how big a pulse of additional carbon that would be. But the confidence limits are pretty broad, and so this is a really important area for us to get better. We really have to have an idea of how big a feedback that's going to be to our warming the planet. We're going to get some help from that. Interestingly, some of my colleagues in Search published a paper this last year in Nature, kind of on the state of our understanding of this problem of carbon coming out of permafrost. And Senator Murkowski in Alaska saw the paper, thought it was really interested, and reached out to us and said, hey, what can I do to help? And so we, of course, put together a call with her staff and our scientists to talk about this. So the good news is, well, I think the first lesson from a kind of foreign policy perspective is just opportunity. You don't know when it's going to be of interest to people in the policy world, but it's a good idea to be ready when they call or write or have a hearing or whatever these are. But I would ask the question, is the response of a single senator to a single paper on one issue the right way to decide how to allocate resources? Because clearly the setup was, what can I do for the University of Alaska? And it would have been very tempting to say, oh, we'll put a whole bunch of money into our program. But it would have been a very irresponsible thing to do, right? Because we put this, there are other issues besides this one that we collectively need to be paying attention to. So I've already answered my own question. It's not a good idea to fund research that way. And the much harder way, but more responsible way, is to have a much broader assessment of our needs. That's involved a lot of players and thinkers. And so when I was in the administration, one of my jobs was to lead the effort to develop a 5-year research plan for the Arctic, covering permafrost and sea ice and ice sheets and coastal erosion and oceanography, et cetera, et cetera. So there are 15 some odd agencies in the federal government that do research in the Arctic. So this is all about bringing them all together and getting their ideas and new ideas from academia and from the indigenous community and coming up with a plan that is the national plan for the coming 5 years. once we had that, we turned to working with our colleagues across the government on a national strategy for the Arctic. It's the first time the U.S. has had a national strategy for the Arctic region. And by national strategy, we're not just talking research, we're also talking geopolitics, we're also talking economics. So in some ways, that was a broader effort, and it wasn't just driven by the science side. Well, this kind of work involves lots and lots and lots of cat herding, and lots of relationship building and maintaining. I guess the take home there, I would say, is I'm not sure how much you're going to learn from understanding the periodic table about working to bring people together who think their interests are different, because I represent NOAA, I represent the Office of Geophysical Research, and I represent. This is really important work, of being able to get people to connect and collaborate even when they imagine they have different interests. So a couple of anecdotes along this line. When we finally got this research plan done and we started figuring out how we're going to actually achieve what we said needed to be done, I got a lot of pushback from my colleagues in the other agencies and people in the White House, because they said, well, we need to put together teams of people, scientists from different agencies, from universities, from NGOs, and they said, whoa, you can't bring on feds into this. This is a federal document. This could only be feds. And I said, well, that seems kind of goofy. I mean, there is so much talent outside of the federal government. Why would we not harness that? And, anyway, it took some time for me to finally figure out, I'm in the White House, I got this cool stationery. And so I very rationally wrote this memo to the agencies that said, you do need to form teams with people outside of the university, and you need to involve them in implementing this research. And the only time you really need to keep them out of the room is if you're spending the government's money or you're writing regulation. You don't have the people who might receive the money or the people who will be regulating them. But most of the time, what we're doing is herding talent, as I say, bringing the ideas together. So that's worked, and we've had very successful collaboration teams of academic scientists and government scientists and others. The other document on the national strategy, that process was really run out of the National Security Council, and they think really differently than people just out in the President's Science Office. They tend to really like to stay closed. And so as we were developing that plan, a couple of us, some of you might have been here when Dave Walton spoke last year. He and I each led one of the elements of this plan, and the national security staff the other. And we both said to them, look, we really need Alaskans to weigh in on this. They are our Arctic state. They're going to have thoughts about this. They have equities here, and what happens with the national strategy. And the national security folks said, we don't have time. We can't bother with that. Anyway, long back and forth, and eventually sort of had to kick it up above everybody's head to senior presidential advisors, which is not something we want to do with any kind of regularity. You burn a lot of bridges if you go over people's heads, but it worked. We did, in fact, go to Alaska with this high-level delegation and spend time getting input from Alaskans on it. Not that they were entirely thrilled with it, but much better than if we had done that. So now I want to turn to my third case. Not all that long ago, we actually had a U.S. president who was interested in science and prone to asking a lot of questions of his science advisor. And one of those questions concerned a series of massive snowstorms and cold outbreaks in the eastern portion of the United States that happened early in his first term. And so he asked his science advisor, John Holdren, what's the connection between these weather events, which I don't want to comment, but the climate. And John Holdren did a very good job of describing what was then a current hypothesis, and to give a concise description of how the jet stream is changing. So the jet stream is this movement of west to east of air high in the atmosphere, moves along in such a way that it not only helps us get to the East Coast more quickly than we get back, but it also corrals cold air in the Arctic. It's slowing down. And as it slows down, like our slowing down river, it starts to meander. And so instead of being this tight band swirling around, it's this kind of wavy thing going on here. And it's going slowly. And so one of the things that happens with these waves is that here we're pulling cold air down along the east coast of the United States. This was the best hypothesis of that connection. So the president really appreciated the clarity and succinctness of Holdren's explanation and insisted that he reprise it for every single senior advisor in the White House. And they liked it so much that they insisted that it get made into a YouTube video we put out that same afternoon. You can find it online if you want. But Holdren also recognized, well, this is a hypothesis, and so he turned to the assistant director for polar science and said, keep abreast of developments and thinking about this topic. Fortunately for me, the scientists who put together the hypothesis and their critics were a short time later meeting in Baltimore to hash out their differences. And that gave me an opportunity to go to that meeting and start figuring out, I'm not an atmospheric scientist, and so cut to the chase here and say, I'm a biologist by training, studying seals, it sort of led to questions about snow cover. I started advising on environmental issues, and all of a sudden I found myself not just advising on seals and snow, but anything having to do with the poles and the sciences. And I think that says it right there, is that you could get a degree in physics, you could get a degree in biology and chemistry, on and on and on. They can say that's the prerequisite to working in environmental policy. But like me, you'll find yourself like, okay, now they're asking the question, isn't it good? So you've got to be a lifelong learner. You've got to know enough about the basics to know what questions to ask. Fortunately, the atmospheric scientists who really speak a different language were kind to me, and I was able to glean from a few days with them in Baltimore the essence of their hypothesis. And what they're explaining is that, okay, here's the equator, right? And here's the North Pole. So they're showing us a latitudinal gradient. And then what they're showing us on the x-axis is the atmospheric temperature at the poles, the equator relative to the poles. And when the poles are really cold, the difference in those temperatures is quite great. And so you can think of the air as being much higher because it's warmer at the low latitudes than at the poles. And so, energy wants to go downhill. So you've got a net flow of air from this high place to this low place. But as it's headed there, it's crossing across a spinning globe. And Coriolis effect takes that south-north flow and makes it a west-east flow. Hence the jet stream. You have a steep gradient, the air is moving fast, you have a steep jet stream. That's a fast jet stream, excuse me. But if you warm the Arctic more than the lower latitudes are warming, that difference decreases. Right? The hill isn't so steep, the movement of air isn't so fast, and you get a slower jet stream at the end of the day. That's effectively what's happening. So how is it that that difference is changing? Well, I told you that the Arctic's warming 2 to 3 times as fast, and I didn't tell you why that is happening. There's 2 principal reasons. One is that, well, maybe the biggest, is that we're shrinking the amount of reflective surface. Right? So if you think about sea ice up in, when I was your age, or the students' age anyway, if you thought of sea ice on the globe as a continent, it would be second only to Eurasia in area. So this is a massive reflector on the top of the globe. And it's reflecting most of the sun's energy back to space. As you melt some of that, because you warm the climate, what's left behind where you melted ice is seawater, which absorbs close to 90% of the sun's energy. So you've gone from being a giant reflector to being a giant absorber. And hence, the ocean is Arctic warming. The ocean is getting warmer, it's melting more ice, and this is an accelerating process. That's one of the major reasons. The methane released from that. Permafrost also factors into it. So we've got this accelerated warming in the Arctic. And we have this phenomenon, we think, of this jet stream effect. So if you imagine that this is a strong jet stream when the differential wasn't so high, and this is a period where the jet stream has gotten really weak and has these big meanders, it's not only causing cold outbreaks on the East Coast, there's good evidence that it's causing weather systems to get fixed in place for a long time. And the drought we suffered here a few years ago is thought to be a direct result of the blocking of weather systems as part of this slow jet stream. But this is a plausible hypothesis, and it makes sense with what we know from the physics. But I said there were critics of the hypothesis, and at that Baltimore meeting, we found that the critics were saying, well, look, it's way more complicated. There are all these interactions in the lower latitudes that are also influencing the global circulation. It's not that simple. And so my colleagues Jennifer Francis and Steve Vavris, who were the ones who really put forward this hypothesis and championed it, they were very good. They said, okay, so what do we need to do to distinguish? So they basically plotted out together, the people with the hypothesis and the critics, what research would we have to do to distinguish between those alternative hypotheses. So, I was able to go back to Holdren and say, okay, here's the thing, is the good news is, or the bad news is we don't have the answer yet. We don't know. The good news, though, is the science community is doing exactly what it's supposed to. It is responsibly working through the issue. It's probably 10 years out before we really resolve this. It helps to have a president who's interested. So when I was advising on seals, I drew on my own science for my head down period. But advising on permafrost and on extreme weather events, that required translating the work of others into formats that can be understood by people who don't have all day to hear the explanation, much less 3 days to go to the conference. So what does this mean for the MIIS curriculum? Well, I think it means that we need to continue thinking about this problem, Jason, and it would be helpful to hear from students and others their thoughts about it. I'll stop there. Yeah.
I have a question about the permafrost specifically. Just earlier today, Jason talked to us about carbon farming. And carbon farming is, just the process of using farms to sequester carbon in the soil. So how can soil both be the problem and the solution?
Right. So the trick is there's a couple ways you can sequester soil, which you sequester carbon. You sequester carbon in living plants, right? And that's so if you have things living in the soil, trees, for example, they're holding carbon. They're just not holding it forever, right? They're holding it for a long time, but not forever. When they die and they degrade, the carbon's likely to get fluxed back into the atmosphere. So partly there's a timing issue there, right, of how long you want to sequester. So that leads to this idea of, well, what if we buried the carbon deep down in vaults and sealed it off? So same problem we have with nuclear waste, we couldn't stash it away somewhere. But I don't know, is there something else?
Well, we were just talking about the new changes in farming systems, kind of cover crops and no-till agriculture and actually absorb a lot of it on the current agricultural systems.
So those root systems and those living things would be taking apart. So does that make sense? I mean, so that, I'm sorry.
Until they die.
Until they die. They're going to take it back down.
Okay.
Yeah.
In your first case, you mentioned that you looked at how the seals navigate. How do they navigate back to their holes? And they have to, or they're going to drown.
Yeah, no, that's one of the issues. So, they have big eyes, which everyone knows that seal. But in the dark winter, under snow and 6 feet of ice, dive with great depths. It can't be very useful. It's quite dark under there. And what's more is we know from not just ring seals, but also porpoises and sea lions, things that when pinnipeds are blinded naturally from the opacities, it's not uncommon to see them. They seem to do just fine. You see them raising pups, and they're obviously still eating. What's going on? How are they doing this? People wondered about this for a long time. I don't know, I'll cut to the quick second, I don't know the final answer, but here's how far we got. Was we figured out that if we blindfolded seals and put them back under the ice, and said, okay, you're breathing now. They said, hell no, at first. And then we kind of forced the issue, blocked access to them. They would reluctantly leave the hole. And instead of like beelining to another breeding hole, they would just start wandering around like they were totally lost and unhappy, and they weren't able to find another hole. And so we take them back up and breed, have a conversation, tell them we're sorry. But one day, just kind of on an inspired moment, we were asking a seal to do this trick, and he was saying, no, you can't do it, I don't know what to do. And I asked my assistant, who was at a hole, the nearest hole, several hundred meters away, we hoped the seal would get there. I said, take that spike you have there, just tap on the edge of the hole. So she did, she started tapping on the edge, and instantly she did that. The seal who's been swimming in pretzels suddenly starts swimming straight towards the hole for several tens of meters, turns swims several tens of meters in the long bearing, makes one more turn, goes straight to the triangle. And range as well. So I think that's a big part of it. They also have tremendous sensitivity of their vibrissae. They have more nerve endings. They have about 10 times the density of nerve endings of their whiskers as terrestrial carnivores, cows and hogs. And so they seem to, there's good evidence they actually use that while foraging. Tail. Yeah.
So apparently we're right now in a warm water block 2.0. And part of the big drought that we had here in California was an effect of the ridiculous residual ridge of high pressure that we had off our coast.
Yep.
And so why isn't this really understood? I mean, we have these anomalies from time to time, but not even anomalies. I mean, the El Niños are not anomalies. They happen once or twice a decade. But this seems to be an anomaly, this warm water blob, and it's heating up a tremendous amount of the Northeast Pacific Ocean, which is kind of alarming for sea life and for many other things.
So a couple of things. I mean, I'm still holding out hope, because last time I looked, it wasn't nearly as deep as the first incredible blob. If it starts getting deep, then I'm willing to bet big money to aim for another drought. So there's some hope that it'll still get broken out, but we don't know that. But to answer your broader question is, think about why it is that we have these long-term variations in solar gain, right? The Milankovitch cycle. So how much heat we take in, never mind how much we hold, and how much we actually receive from the sun. A Hungarian mathematician figured this out for us a long time ago. Has to do with our distance from the sun and our angle to the sun. And so there are solar cycles, or now called Milankovitch cycles, that are on different periods, 44,000 years, 10,000 years, 4,000 years. And so if you imagine that these different cycles are influencing how much solar gain we're getting, and you can imagine those cycles could be out of phase, in which case they're more or less canceling each other out, or they could be in phase, in which case they're amplifying each other's signal. Well, I think it's much the same thing. So the blob is not just a function of how much heat we're taking in, It's also a function of circulation patterns, it's a function of upwelling, is there a need, etc. So it's a scientist's way of saying it. Yeah.
On a similar topic, you described these shifts in atmospheric circulation. There are also oceanic circulation patterns. How are they being affected? There must be an interaction between atmospheric and marine patterns.
There are, and that's very much how the whole search program got started was, Andrew, is it something I said? Sorry. The atmospheric scientists started noticing in the Arctic in the late 90s that they were just seeing patterns they'd never seen. Same thing with the oceanographers, and so they started talking and comparing notes, and then pretty soon they pulled in the ecologist, and that's sort of how we got going. But you're right, I mean, so there is, I can send you a piece if you want, that some of my colleagues wrote, looking at the impact of sea ice loss on North Atlantic ocean circulation and hence atmospheric effects and hence Greenland ice melt, which changes the oceanography. So that would be one example. As the atmosphere warms, we've been melting unprecedented amounts of the surface of Greenland. That's fresh water that's flowing in the Atlantic that didn't used to be there. And then fresh water on the surface has a lot to do with the driving of the conveyor belt. So there are those kind of feedbacks, but they're complicated, and I don't think we haven't figured out as well as we. Well, I don't know. I mean, on the other hand, I'm really impressed by. So we just did a big conference at the National Academy of Sciences last month, and we brought in Arctic scientists and indigenous people and policymakers from around the world to sort of look forward, like, okay, what is it we ought to be doing? What do we need to know? And it was pretty heartening to hear that the science presentations, partly because we need brief, but to get right to the point. But we have one, and I can point you to this on the web if you want to see the video of it. In fact, the chair of my steering committee is an atmospheric scientist in Boulder. She models sea ice for the community Earth system model. So this is one of these models that takes everything in the Earth system and links it together. So that we had her kind of thing in that sea ice. And she did, in that talk she gave us, was really a really clear explanation of how global models work, how they connect. It's highly accessible. And, so if you go to the search website and you look for Arctic Futures 2050, you'll see the entire program for each one of those talks. There's a video that you can pull up. Rika Holland is the author. She found the best explanation I've ever seen. This is how global climate models actually function. Still a really interesting question, but it's the best I can do. Let me see it. Yeah.
I got a two-point question about the critiques when they were talking about jet stream and warming optics. Is it about distinguishing correlation and causation? The second part is that maybe dealing with distinguishing between correlation and causation when talking with public, the general public or policymakers out of joust.
Great questions. So I kind of skipped over, but I said that they have a plausible mechanism. That was this explanation of the change in the flow of air south to north and then west to east when Coriolis effect comes. So that's the plausible mechanism. So that's not just correlation, but exactly what the critics, to your point, the critics say is, well, show us the data. We want to see this in action. And the argument, some people will say, well, you know, we think this is a new state in the system, and it's just shifted. And if that's true, we don't have an observational record with which to test it. And that's why I told the President's Science Advisor, it's going to take at least another decade where we can start to see, does this hold up with when things shift to colder or warmer? Do we, in fact, does the system respond the way this model predicts? But you're exactly right. I mean, I mean, in this case, we're not basing it on the correlation, but we don't even have enough observation data. It actually starts with first principles. The second part of your question had to do with public perception and
General public and policymakers, I may not be as familiar with the difference between something that's causing something correlating.
so I don't know if everybody heard that, but the question was, well, okay, the general public often has a hard time distinguishing correlation and causation, and maybe policymakers do as well. Actually, what I find mostly is most policymakers are more sophisticated than that. They don't have a hard time understanding something like that. I'm sure there are exceptions, but I think, you know, that's, I would guess I would say that's the sort of thing, back to everybody here, is coming up with sort of intuitive examples. So if I got that question from, you know, general, maybe a hostile audience member, I don't know, somewhere, didn't even want to believe this climate stuff, I probably wouldn't talk about these processes. I would think of an example that had to do with that person's everyday life. I want to know, what is it where you could understand the difference between correlation and causation. You know, there is a correlation between the number of people in this room who believe that climate change is driven by people and the people who breathe oxygen. Every one of the people in here who believes that climate change is driven by human activities breathes oxygen. We got it, right? You know, so I know that's not, it's kind of trivial, but that's the best answer I can think of, is try to talk to you about it. Yeah.
There's a lot of times people talk about the tipping point. And it seems that we keep rolling over each tipping point. We don't know, and we're seeming to try and study where that point is.
Right.
But it would seem to me we passed it before we knew it.
Yeah, so I think it's an appealing concept of like this point of no return. But again, I just use the term point. I'm really talking about processes. And so what we're really, I think, talking about in all those cases, is this a process that can be reversed? And is it a process, more importantly, can be reversed in a humanly significant amount of time, right? So I think the point is the part that gets us. Was it 2015 or 20? Well, no. None of the tipping points I can think of makes sense if you think of it that way. But if you think of that, once we've gotten so much sea ice melted and it's accelerating, it's going to be really hard to draw it now. So, yeah, I think it's sort of a term that was useful heuristically, but it's kind of what its usefulness.
Maybe I can just add to that real quick, because there's a lot of people talking about that. There's these new IPCC saying if we don't do by 2030, we have 10 years left. So it's, again, the heuristic is always these kind of deadlines, these thresholds, and it's a very unhelpful way to think about it, right? Like every 1/10 of a degree is going to matter a huge amount to millions of refugees, millions of species. So we just want to think about this as kind of intensity. Like we're on this path of really intense warming. We want to just dial it back as much as we can. It's not a threshold effect. It's just every bit we can do to dial it back is going to help future generations and help reach some kind of equilibrium. And then we don't have to get into this, oh, we didn't do it by 2030, so give up. Right? There was never going to be a point where we can't do more. Right? That's kind of the way I think.
Yeah, it's a really hard one, because it gets harder and harder to remediate the damage the longer this goes on, right? And so you don't want to tell people, well, we'll figure this out later. So I understand why they do it, but I have the same issue with the use of these, well, by this date, because then that's what the journalist sees on, and that's what inevitably people want to understand is, does that mean we missed it, so why ask you to drive off into the sunset? Yeah.
Just a quick question regarding the politics part. So you said that the current, let's say, administration has
I don't think I mentioned the current administration.
The previous administration was better receiving information from the scientific side, let's say.
I guess I didn't find that.
Do you think there might be a direct effect of the current administration regarding the Arctic?
Oh, yeah. Yeah.
What's your question?
Oh, sorry, I think the question, let's see if I got this right, that comes from me, is do I think that the current administration has had an effect on the Arctic? I think you mean that.
Yes, exactly. Yeah.
Certainly, but it's also global. I mean, the whole idea of, you know, encouraging fossil fuel development in the Arctic, that's not going to help very much at all. But it's going to be broader than just in the Arctic. You know, Dave Bolton, when he was here and when we worked together in BC, you know, talked all the time about, well, you know, the Arctic's traditionally been an area, region of peaceful coexistence, stability, and you know, we expect it to continue. At some point I realized, oh, he works for the State Department, it's his job to say that, right? You know, he's not supposed to say, oh, things are going to get a lot worse. But in fact, you know, this strange foreign policy behavior that we're seeing this is a really bad time to not be figuring out how to live on an ocean together with 8 other countries that is increasingly being more like the Mediterranean. So one of the things that became clear when I was working in the Obama administration is that the Russian they saw this very differently. You know, we've got one coastline, right, that has a small part of the Arctic is our coastline. Half of the whole Arctic is their coastline. It's huge. And it's been naturally defended forever. And all of a sudden it is. And that's very scary. So suddenly we see this great interest in militarizing the Arctic. And we're going to say, oh no, it's peaceful, it's stable. So this is not a good time to have amateurs running
Are the policymakers really as ignorant as they're behaving, or are they just kowtowing to the commander-in-chief? Do you think that there's true ignorance, or are they just...
Yeah, so it's just like any collection of people you come across. There are people who are ignorant, and some willfully and others not. And there are people who are more thoughtful, and there are people who are extremely thoughtful and make an effort at it. And you know, in that sense, our representatives reflect us. And certainly in Alaska, I would say there's a pretty broad range. There's only 3 congressional people from Alaska. I'm not going to name any names, but there's at least one who's willfully ignorant, and there are others. There's another that's I don't necessarily agree with the person's politics, but it would not be proper to refer to the person as ignorant. Witness, you know, that person, which only name list whose initials are Lisa Murkowski, reading Nature and asking scientists questions about it. And the other person is somewhere in between. So, I mean, I think that's representative. I think that it's not helpful to think of, in my view, to think the policymakers is ignorant or not ignorant. I would just say they're on the spectrum like all of us, and we should. Jason doesn't agree. We have fights about this all the time. Yeah.
Given the hostility of this administration to science, are you discouraged, or your colleagues discouraged?
You know, it's really waxed and waned. In putting this together, I came across a slide for a talk I'd done just after the 2016 election, and some colleagues asked me to sort of spend a whole talk on should we all freak out, or is it all going to be okay? And when I came across on my hard drive was an article that Neil Lane, who was a previous director of the National Science Foundation, and he'd been the president science advisor back in the day. I think he's now at Rice University. He wrote an op-ed saying the president needs to get a science advisor, serious advisor, he needs to get one right away. And this name took over 2 years to get a science advisor. The good news is the science advisor that he got is a credible scientist and a pretty decent person. Unfortunately, he's not dual-hatted as the way John Holdren is. So John Holdren was both the President's Science Advisor and the Director of the Office of Science and Technology Policy. So Dr. Drogemeyer is the current advisor, is the Director of the Office of Science and Technology Policy, but he is not an advisor, so he doesn't have the daily access that the previous one did. So the good news is we have a credible President's Science Advisor. The bad news is he doesn't have a lot of access. On the other hand, the good news is, you know, my colleagues in the Global Change Research Program, it's a federal agency, it's a sister organization to the group I ran that encourages Arctic research policy. The Global Change Program put out a national assessment that pulled no punches, and they didn't get censored. They didn't, you know, get. But then there's cracks. I recently saw it was the Bureau of Ocean and Energy Management put out given themselves a free pass on environmental assessment work for offshore oil drilling in the Arctic. And it said flat out there that something like, well, climate has changed and it'll be fine. And something. So it can sneak in, but I think I just, on the other hand, you know, we could be a tweet away from complete disaster. Yeah.
Two questions. One is, you thought that the big problem with the permafrost melting was methane.
It is.
Oh, you were talking about carbon, but it's also.
So, I'm sorry, when I said, thank you for catching that. I was doing the bad science thing of using shorthand. So when I say carbon coming out of methane, coming out of tundra, I'm talking about methane and I'm talking about CO2.
Okay.
Those are the forms of carbon.
So my other question is about your seals, and I'm wondering, you know, it looks pretty dire in terms of habitat loss, and I'm wondering if anyone is doing any research or finding anything promising about adaptation options for the seals. I mean, is there...
No, I mean, I was such a head-down scientist for all those years, but I actually kind of liked the fact I didn't really care about ring seals because nobody were feared. I just
You and your dog.
did me and the dogs. We did our research. And everybody else in the hut was freezing because it was really cold. And one bottle of it was a good one. But no, it's always been sort of an area where we haven't allocated sufficient resources, and it still is. And although I have to say, having worked in trying to herd the interagency process, I've become a lot less willing to pound my fist on the table and say, we got to do more seal work, because I think, yeah, it's important, but I'm worried about this methane. There are a lot of things that are higher on the list now.
But there's no sort of options or hope for new patterns for the seals.
Oh, there's great hope. I have colleagues who say, oh, well, they'll adapt. They're really hopeful. They have no reason to base that on.
They'll move to Manhattan.
No evidence. Right. I think Rachel, and then you.
So how important is it to like simplify things for policymakers? I mean, as the Center for the Blue Economy here, we're convening the California experts in business and academia and research around the Blue New Deal. We want to take this to the East Coast, or we want to make this potentially national legislation. But how important is it to have that very, very simplified version versus the underlying? Because I can see this having started out as like an 8-point plan, Blue New Deal that Jason and David Hillbart co-authored, it now getting really, really, nuanced and intricate as we introduce more people and more players. We want to make it broader and broader, but then how important is it to like simplify it back for the public consumption and for legislators?
Yes. Which I mean, that is exactly the right question to ask. Sorry for being funny, but the fact is, there's no getting away from it. It's audience specific. And so what we're all tempted to do is say, okay, we're going to write a plan, we're going to write a research plan, or a Green New Deal plan or something, or a Blue New Deal plan, and somebody, inevitably in the conversation, I bet this happened the other day, somebody at some point says, well, wait a minute, who's our audience? And that inevitably comes up, and then people go, well, and it turns out different people in the room have different audiences. Some say, well, it's the general public. Say, no, it's the state legislature. No, it's journalism. They're our amplifiers. And they're all right. They're all correct. So then the temptation is saying, okay, well, we're going to kind of write it as our primary audience is the legislature, but we're also going to recognize we have these other audiences. And you end up with this not very good compromise. And so the fact of the matter is, those of us who are scientists, we were on a field trip the day the lesson was taught in the English class, know your audience, know your audience, so we don't have any friends, which is play to the same geeks all the time. But I would say it's more complicated than that, in that you do need a different version of that for the state legislature, and yet a different version for the county supervisor, and a different version for the press. And so it's just a lot of work. And so there's a really interesting, some of you may be familiar with a philosopher of science named Thomas Kuhn, and he wrote a book back in the 60s called Structure of Scientific Revolutions. And he was interested in how paradigm shifts happen in scientific thinking. And in the course of describing how science naturally evolves, he explained that if somebody has come up with a new paradigm, they've like shifted the way we think about the world, they by necessity have to write and talk in broadly accessible terms because there are no specialists yet. Right? Everybody is kind of on a level playing ground. Think of Darwin in The Origin of Species. He didn't write that to evolutionary biologists. There weren't any. He wrote that to learned peoples. Fast forward 100 years, you pick up an evolutionary textbook and you go, yikes, I got to learn this incredible vocabulary and all this minutia. And what Kuhn pointed out was that this is just a natural evolution in the science. A new paradigm comes along, it's very broadly accessible. People start going in and trying to figure out the details and elaborate on it, and they become more and more and more specialized, and they talk to an hour with people. And then you have evolutionary biologists 100 years later who can't talk to physicists, who can't talk to chemists, who can't talk to environmental scientists. So a lot of what I come to think of our challenge for people working in search is we now need to reverse engineer the whole thing and go from, I have all these specialists who know a lot about permafrost fault and where that's headed, and a lot about Arctic oceanography, and a lot about atmospheric chemistry. But now I've got to get them back to talking to a broad audience. And so they could easily talk to a journalist, they could easily talk to a senator or a congressperson or a high school student. I think that's what has to happen. We just have to get over this idea that it's easy to just find one catch-all document. And those briefs I referred to, those are targeted mainly at policy staffers who we recognize are, as I say, a sophisticated audience. It's not dumbing it down. It's just making it so you don't have to take all the courses I took to understand what I did with seals or whatever else. Does that help? You back there. So.
Yes, I had a question about the permafrost. There have been a lot of stories regarding zombie pathogens from the release of the permafrost in the media.
Mm-hmm.
Classic example would be, anthrax being released from reindeer carcasses.
Right.
I was wondering what research, if any, you have come across in your experiences being in the Arctic profession.
So the National Academy of Sciences has asked this question a lot, including the Polar Research Board that I serve on for the Academy. And so we were exploring what kind of a study we need to cause to happen. This is what the Academy is good at. That will sort of answer that question. Is this a big problem we need to worry about or not? That's an oversimplification. And along the way, we found out, well, the Europeans are asking the same question. So the good news is that there is a group that's formed that's now going to be Europeans and the US, and probably other countries, but I'm not sure. But in any case, they're going to meet in Berlin this coming year to start trying to answer that question. What I would say is, well, I'll make one observation, one prediction. The observation is that the case that you cited is the one that's mostly ginned up people's interest. For people who don't know, last year, or maybe it was the year before, I don't remember, some reindeer were were thawing out of permafrost in Siberia, and they were infected with anthrax, and it got into live reindeer populations. And hence this idea of a zombie apocalypse. These are not Pleistocene reindeer. These are much more recent reindeer. So this is as though you buried a sick cow in your pasture, and 5, 6, 7, 10 years later, it thawed out and gave your current cows anthrax. Which isn't to say that you couldn't have pathogens that in fact had been frozen for 10,000 years come out. But then so my prediction though is that this is probably not very high on the things we need to worry about. So there is a fairly reliable principle sort of in evolutionary biology, and it's called the proven parasite hypothesis, which is that if you're an organism that lives off of other organisms, it's kind of a good idea not to treat these things, because you destroy your host, you have a host. So it's not to say that you could lose a lot of people or a lot of reindeer or something to an epidemic, but this kind of idea of the end of civilization might be, and obviously people think about it more sophisticated than that, but sometimes you read the paper and this is going to be a little bit.
I'd like to build off Rachel's question, and just talking about us students who will likely be future policymakers. Do you have any advice from your experience when it comes to translating science into policy? What works, what doesn't work? What we should know going into the workforce?
Yeah.
Tips and tricks?
Yeah, so I think I would avoid being too narrow. So if somebody comes into policy as a generalist, depending on the topic, they're going to have a lot of catching up to do. If it's a narrow field where he knows water chemistry, he understood chemistry. On the other hand, if you train somebody in water chemistry and give them a PhD, and along the way they stop taking foreign language classes and art classes and humanity classes and literature classes, it's not going to communicate very well. So they may know a lot, but they're going to be handicapped in terms of being able to know their audience and deliver to that specific audience. So what does that mean? I think I would say of the two errors you could make, I would don't make my error. Don't be a PhD scientist. Don't think that's the best route. It's not necessarily a bad route. But if you are coming in from the generalist point of view, then you have to be aware you're going to have to really do a lot more work, depending on what office you end up working on, what topic. Some of the best, so most of the people who I worked with in the Office of Science and Technology Policy at the White House were PhD geeks, experts, and most of them were really good, otherwise they wouldn't, get to stay if they have very clear process. You just didn't get any really good stuff. But we also had some remarkable people who did not come from a science background. I remember one guy who worked on satellite observing systems, and he was an expert on it. And he knew everything about our satellite assets, what they were used for, and he was, I'm trying to herd all the people working in the Arctic, he's trying to herd all the agencies, NASA, and all the Department of Defense, et cetera, who have satellites running around collecting data. And he was remarkable at it, and he knew the stuff extremely well. His background was in conflict negotiation, worked in the Balkans. By some strange path, he ended up at NOAA and ended up working on satellites and then got seconded to the White House. We had another guy there, a brilliant guy working on the tech side. He's a playwright, really successful playwright, et cetera. But these are great minds, and these are people who can learn on the job. So I guess the main point is you're going to be, you should be thinking about how is it that I will not finish my education degree, because that will fairly constrict you. So figuring out how you work, what is it that you need to figure out what the hell are these atmospheres scientists telling us about this, and having to figure out when do you just have to sit down and crack a book, and when do you find the right members and tutors. Does that help?
Sure.
Yeah, good. Okay, I get a cut. Yeah.
Do you know much about the gray whale die-out this year?
Not this year. I don't. I haven't kept up with it. I've done my fair share of dead gray whales trying to figure out what killed them and things. But as far as I've been able to glean, I haven't done any deeply. The best hypothesis is they're not getting enough to eat.
Yeah. Is Baltic Sea ice?
Yeah, it could be. So their main feeding ground in the summertime for most of the last few hundred years in whole life, professional life, is in the northern Bering Sea, which is an incredibly rich place, bottom deep water. And the walruses also like to vacuum up that bottom, as do stellar tigers and as do bearded seals. So everybody knows how to eat a lot of meat about that cafe. And as populations of walruses and gray whales come back, large numbers, they're just themselves putting a lot of pressure on that. Both those species are all moving up as the ice retreats further and further up the Chukchi, which is also pretty good that they kind of but yeah, I can speculate. That's not what you're asking.
All right, I think we'll wrap it up here. If people want to stay and just say hello and introduce yourself to Brendan, feel free, and thanks for coming out.